This next section is mainly combining a few topics and working out some problem solving. This is another video where we aren't really learning anything new. We're just kind of combining a bunch of definitions that have been leading up to this. So we're going to be talking about how stoichiometry relates to the enthalpy of reaction. So what are the specifics of what we want to do? Well, we have already discussed the delta H of reaction, but here we're going to talk about how that is affected by the amount of the species. So far, we've just been doing everything for the reaction as given. Nothing here is particularly new, as this is all done through the exact same stoichiometry that you've learned in high school, 1A, 1P, and all of your chem classes up until now. It's worth discussing how to do it in this particular context and showing you some examples, though. Let's first do a quick review. We know that delta H is the amount of heat that is given off in a reaction. What we haven't discussed yet is how these properties are related to the amount of the species. Logically, we know they must be. If you look back on our previous videos, all of the amounts that I gave you were in moles. And this is because the enthalpy of a reaction is definitely based on how much of the reaction we started with. Think about a bonfire. If you react one piece of wood, you're going to get a certain amount of heat. If you react 20 pieces of wood, you're going to get more heat. This will require excess calculations for us. Now, a quick term that we should review here is extensive. Remember that a property that depends on the amount of species is an extensive property. Since enthalpy depends on the amount of a substance, it is extensive. If you want a more full review on this, go check out the video where we talked about extensive versus intensive properties. The per mole that is listed when we're talking about the delta H can or may or may not necessarily be for 1 mole of every reactant. Now, let's take a look at a reaction and think about how this may or may not be 1 mole. If I give you this reaction and I give you the delta H, look at your coefficients on the reaction. It can't be for 1 mole of each species because 1 mole of the propane does not react with 1 mole of oxygen. 1 mole of the propane reacts with 5 moles of oxygen. So when we list this kilojoules per mole as our delta H, we have to define what type of per mole we're talking about. And the way that it's defined is moles of the coefficient. So for example, the delta H given is for 1 mole of propane and 5 moles of oxygen in order to create 3 moles of carbon dioxide and 4 moles of water. Now, that's going to give us a way of doing this for any species, for any reaction. You're just going to multiply by the molar coefficient. This makes a little more sense when we do some examples, so let's do one. Let's do a 2-part example. Given the equation that I have here and dH of the reaction, how many moles of butane would be needed to create a particular amount of energy that we want? Here I've asked you for 1.5 times 10 to the 3rd kilojoules of energy. Let's change the units on delta H just a little bit to make it a little bit more obvious how to do this. We know that the delta H is listed as kilojoules per however many moles of the coefficient is given. For butane, that's just 1 because the coefficient in front of butane is 1. So we can rewrite this for this reaction and say that delta H is negative 2,658 kilojoules per mole of butane. When we go to do the next step, we're going to have to alter how this works just a little bit. So now there's several ways to do this next part. As with most of our stoichiometry, pick the way that works for you. How I'm going to do it is I'm going to write an equation that says that our delta H of reaction multiplied by an unknown amount of moles is going to equal our desired amount of energy, our 1.5 times 10 to the 3rd kilojoules of energy. So from here, we can solve for moles to get our answer. We have our energy that we want. We have our energy of the reaction times by our unknown. So now we simply solve for our unknown. We divide the negative 2,658 on both sides, and we get our 0.56 moles of butane. And that's our answer. Now when we go to do the next one, there's going to be a little bit more complications to it. It's going to be very, very similar, but in this case, I'm asking about a product that is produced. I've also asked you for mass as opposed to moles, which just adds in one little extra step. Now, in this case, the stoichiometric coefficient isn't 1 anymore, it's 4. And so the delta H is per 4 moles of the CO2. So now we can pretty much do the exact same thing that we did before when we rewrote the delta H in terms of the thing that we cared about. But we need to be careful that we write it in terms of moles carbon dioxide. And so we're going to have a divide by 4 in there because it's not per 1 mole anymore, it's per 4 moles. From here, we can write out the same sort of reaction where we say, well, we want the 1.5 times 10 to the third kilojoules of energy, and we know that that's going to equal our delta H of reaction times by some unknown amount of CO2. So now we solve for our unknown, and we get our 2.257 moles of CO2. So very, very, very similar to the last one, just we had to divide that initial heat of reaction by 4. Now that we have our moles of CO2, the next step you do using the exact same way you've been doing it for weeks and weeks, maybe even years and years, and change our moles into grams using our molar mass that we get from our periodic table. So we multiply by our 44.01, our molar mass from our periodic table, to get our final answer. Now this is just one example of using stoichiometry with our delta H. Of course, as with all stoichiometry, there are millions of different ways that we can combine this. So the new important part to add into all of the things that you've already been doing is that the delta H is per however many moles the coefficient in front of the species in the reaction says. So for a quick review, delta H is the amount of heat that is given off during a reaction, or absorbed, of course. It is an extensive property, which means that it depends on the amount of the species that is being reacted. When we calculate the delta H of a reaction, it is calculated per stoichiometric coefficient moles. So if there's a 1 as a stoichiometric coefficient, it is per mole. If there is a 4 in front of as a stoichiometric coefficient, it is per 4 moles. And of course, we did an example with propane and oxygen reacting to form carbon dioxide and water to say that the amount of delta H given is for 1 mole of propane, 5 moles of oxygen, 3 moles of carbon dioxide, and 4 moles of water. Now, of course, these are all experimentally determined with calorimeters, and so you can go back to the calorimetry video if you want a review on how we actually go about doing this experimentally.